Alright, this is the second installment to the forces unit. Now we're going to talk about Newton's second law. We talked about the first law before, which was F net equaling 0. A body at rest tends to stay at rest, and a body in motion tends to stay in motion. The second law is kind of the continuation from that. Whereas acceleration was 0 before, now we have something that's accelerating. So Newton's second law. The acceleration of a body is directly proportional to the net force on it and is inversely proportional to the mass of the object. The object accelerates in the direction of the net force. Net force. Now, net force we'll spend a lot of time with. Net force is not an actual force. It is all the forces added together, remember. So it's not a new force. It is just all the forces added together. So the first sentence gives us the relationship between the acceleration and net force and mass. So we get that it is directly, so that's why with the net force, and inversely, so we're dividing by the mass. The second sentence tells us it's a vector, a direction. So we get that vector direction in there, so F net is a vector. Acceleration is also a vector, as we know. Now we got to make it a constant. Now, if you're handy with math, you might understand why we have to do this. If not, don't worry about it, but we have to give some sort of constant. Funny enough, Newton actually came up with all of this, so he just said that the constant was 1 and then proved it to be so. So that makes our life a little bit simpler because it basically disappears because k is 1. And we always tend to use this equation written like this, as F net equals ma. This is only for the net force. No particular force can equal ma, just the net force. So, in general, can't say this too many times, if there's a net force on an object, it must accelerate. Units. We said the units for force, so force we said was newtons. Now mass has to be in kilograms and acceleration has to be in meters per second squared. So let's look at this equation and see how the unit is related. So we would say that 1 Newton is equal to 1 kilogram times 1 meter per second squared, which in terms of units means that a Newton is equal to a kilogram times meters over seconds squared. That's just a little bit of relating our base units in the SI system to the Newton. You don't have to write kilogram meter per second squared, but you do have to know that that is equal to a Newton, and it will help you later on. Let's take a look at some problems. So we've got Newton's second law with Lisa and another girl, Sarah. So Lisa's holding a stuffed bug with a mass of 0.30 kilograms when Sarah decides she wants it and tries to pull it away. So Sarah's not a nice person, but either way, if Sarah pulls horizontally on the dog with force of 10.0 newtons and Lisa pulls on the dog with a force of 12.0 newtons, what is the acceleration of that dog? So you can see that I've listed out my givens. Step 1, any problem, always. Forces, there's always a step 2, and it's always the same, and it's always a free body diagram. You'll notice my squares don't always look very squarish, but it doesn't matter. We're just using it as an object. Now, the forces that were being applied to the dog, because we're worried about this thing right in here. Not Lisa or Sarah, just the dog. So if Lisa's on the left, she's pulling this way. So that's the force of Lisa. And then we've got Sarah pulling on the other side, force of Sarah. Those are the only forces that we're going to put into our diagram. Now, we don't know which way is going to be which, so we're just going to stick with our normal positive, negative system, right positive, left negative. We want the acceleration. Newton's second law problems always go to F net equals ma. That's our equation. F net equals ma. Okay. Well, we want the acceleration. So let's just rearrange that equation. So we get acceleration is F net over the mass. Okay. Now, well, we don't have F net. We've got the force of Lisa and the force of Sarah, but we know that the F net is also, see, F net's two things. It's the sum of all the forces, but it's also equal to ma. So we can say that F net is the same as our vectors FL plus Fs over the mass. We don't want to work with vectors. We just want to apply our directions and lose our vector signs. So if we lose our vector sign over here, Lisa's pulling towards the left. So she's actually going to have a negative force, and Sarah gets a positive force, and we get our mass. Now we plug in our numbers. So we got minus, and Lisa's 12.0 newtons, plus Sarah, so that's 10.0 newtons, all over the mass of the dog, which is 0.30 kilograms. And that gives us, so that the acceleration is negative 2.0 newtons over 0.30 kilograms, which, putting that in your calculator, is negative 6.7 meters per second squared. There we go. That's it. The key to these problems is starting with F net equals ma, and then knowing that F net is the sum of all the forces. You can do it a few different ways. I'll show a different way in class how to do the problems, but F net is your key. Always start from there and then put in what you know. Take a look at these wonderful problems here between the textbook and workbook, and go over some practice, and we'll see you in class. And as always, physics remains to be awesome.